Here are some solutions to the Chapter 12 in-class synthesis problems. Our first question is this one, and we want to think about how we can make those two molecules. And we know that we have two carbonyl species. We have a 4-carbon species here, and we have a 6-carbon species there. That's supposed to be a 6. And at the starting material, of course, we have a 5-carbon species. So we need to add 5 more carbons somewhere along the lines, and ultimately end up with these two aldehyde species. And so clearly we're going to cut some bond in order to have our 4-carbon species and the 6-carbon species. And I think we're going to have an alkene between these two carbons in our penultimate starting material. So we can redraw. There's the alkene. Here's carbon 6, and this is the dotted carbon right here. Let's make that a little more clearly. And then I need to add 5 more carbons here. 5, 4, 3, 2, 1. And if we take that, subject it to O3 DMS, 2 different steps, we should be able to make cleavage of that alkene and end up with 2 aldehydes. So now we have a new synthetic target, and it has a total of 10 carbons. And we started with 5. We need to add 5 more somehow. We know how to add 5 carbons, and I think we can do that right here. Deprotonation with NaNH2, followed by a 5-carbon chain with some leaving group on the end. 1, 2, 3, 4, 5. Gets us to that alkyne. And of course you see that the triple bond is in the same position as the double bond. That's a pretty good sign that we're on the right track. All we have to do then is reduce that. And in this case, it really doesn't matter which method we choose to reduce from the alkyne to the alkene. We could have used H2 and Lindlar's, because of course we don't care what the stereochemistry here is, because we're going to cut that double bond and end up with 2 aldehydes where we cannot observe what the stereochemistry was from those aldehydes. So it doesn't matter what we choose here. We could choose Na and NH3 liquid, or we could choose H2 and Lindlar's. So that's the synthetic route here. I'd count that as 3 steps. And working backwards again, we discovered that the need to do the ozonolysis on this particular alkene. Question 2 is here. So we obviously have a ring, and in here we have 3 carbons on the ring. Here we have 5 carbons plus the ring. So we need to add 2 carbons somehow. And more importantly, we have a methyl ketone right here. That's a pretty good indication that we're going to be doing one of 2 possibilities, right? We could cleave an alkene right there, which involves adding more carbons and then cutting them off, or we could use, out of Chapter 10, the way to make a methyl ketone is starting with that terminal alkyne. I think that's probably the best way to go here. So of course that's H2SO4, water, and our mercury sulfate catalyst. And again, we have, keeping track of our carbons, we still have our 5-carbon chain, and except that using these reagents, we've turned that terminal alkyne into the methyl ketone. So that's my last step. So now the question is, how do I get from this alkene to this alkyne while adding 2 carbons? We know how to add carbons, right? We use an alkyne that we deprotonate, and then we alkylate. So could we make this bond using that technique? Could I make that bond using a deprotonated alkyne along with some primary halide as an alkylating agent? And in that case, our primary halide would need to be on carbon 3 of our chain, which is the same carbon as this one. So can I put a primary halide there, is the question. Well, I think I can. If I use HBr, peroxide, I get this. That gives me a primary halide right there, and I can add 2 carbons by bringing in a deprotonated acetylene. There's no reason you can't bring in the acetylene as a reagent instead of producing it on the paper like this molecule was produced. So if we just add this acetylene to this primary halide, that's what we get. There's no reason we can't bring this in as a new source of carbons instead of, as we've gotten in the habit, producing the alkyne from our starting material, like this one, and then bringing in the alkyl halide. So don't get caught up in a certain order that things have to be done in. You can do it backwards too. So this is, again, is a 3-step process. We make the primary halide, then we bring in our nucleophile that extends the chain by 2, and certainly we could have an R group here too, right? We're not limited to acetylene in this case. R could be, in our case, we want it to be H, but we could certainly have a 4-carbon or a 10-carbon or a 27-carbon R group here if we want to. So we're not going to do that in this case. I just wanted to point out that you're not limited to acetylene in this technique. And then once we have our terminal alkyne, we can create the methyl ketone using the mercury sulfate catalyzed addition of water. All right, step 3, or problem 3, we have, let's see, 4, 5, 6, 7, 8, 9 carbons. And then I have 9 carbons plus this one. If you want to count that as an additional one, you could count it as 10. I would say let's count this as 9 carbons plus the CN, because the CN we know can be added as a nucleophile, and that probably is going to be our final step. So if we add CN as a nucleophile to something that looks like that, I think that's going to be our last step. And now we can start to sort of get back to our starting material. We observe the need to somehow add a chlorine to the end, and actually let's make this a bromine, because I think there's an easier way to do that using HBr and peroxides. So of course we can add HBr and peroxides to that alkene, and that will give us the primary bromide on the end. That's well suited for an SN2 with the nucleophile CN. And now the reaction becomes just migrating the double bond, just like we saw at the end of chapter 9. So we could add HBr in a Markovnikov addition here. That's going to add to the more substituted carbon. And then we could eliminate using a large base. That's going to give us the Hofmann elimination. So that migrates the alkene around the molecule. And then again, we can add our leaving group to the end of that alkene and then displace it with cyanide. So this is a simple combination of moving the leaving group and moving the double bond. Question 4. Let's switch colors here. So we have a 1,2 dihalide here. The interesting thing is, though, that's a cis dihalide, as it looks like here, right? So if we were to do this, we would expect cis addition to this alkene to get our product. However, we know that dihalide addition is a syn addition. I'm sorry, I'm misspeaking here. This is syn. We know that dihalide is anti. And so this alkene plus the dihalide would not give us the syn addition. It would give us the anti, and that would give us sort of a dash on one side and a wedge on the other. So we can fix that, though, I think, by starting with the Z alkene. Because the Z alkene, and let me erase this arrow here, the Z alkene will still add Cl2 anti. It will get us this setup, right? And of course it's plus minus, and I think this probably should be plus minus as well. So you agree that the Z alkene will add Cl2 in an anti fashion. It'll look like this, but what if we rotate around that single bond to stretch the chain into the more zigzag pattern that we're used to? How would that affect the dashed chlorine? Would it still be a dash as it's attached to this carbon right here, I think it would be a wedge. You can convince yourself of that by assigning stereochemistry to here and assigning stereochemistry to here. Hopefully it's the same. So here you see that if we start with the Z-alkene and we add Cl2 anti and then we rotate a little bit, we can get it to look like the desired product. So let's do that. And we know how to make Z-alkenes versus E-alkenes, so that's not really a problem. And of course, we can also observe that there are 8 carbons here. There are 6 carbons here. So we need to add 2 carbons somehow. That's pretty simple to do. And of course, making the Z-alkene is just H2 Lindlers. And then adding 2 carbons, we know how to do that in our sleep. Deprotonate, add 2 carbons. So this is a simple 3-step sequence where we add 2 carbons as an ethyl group on the end of our alkyne, and then we hydrogenate or reduce the alkyne to the alkene, and we do that in a Z fashion, or a syn addition of H2. Then we add the Cl2's anti to this alkene, the Z-alkene, which can rotate to make it appear that the Cl2's were added syn, even though they weren't. So don't be confused then by this seemingly weird syn addition of the Cl's. It is an anti depending on the stereochemistry of the alkene that we start with. Alright, question 5. Let's switch back to blue. I like that color better. So here is a strange functional group that at first might look very unfamiliar, something like we don't know how to make. But if you remember, in chapter 9 we learned how to add 2 OH groups across the alkene. We make a diol, and we used as a first step MCPBA. Second step was ring opening with acid. So remember that the first step made this thing, and then we ring open it with acid. This is an epoxide, and this is chapter 14. If you want to read ahead, you'll see that in Organic 2. So we know how to make this epoxide, even though we never really thought about that as being the end product. So MCPBA with no second step would leave us the epoxide. And we know that MCPBA needs an alkene to react with in order to make the epoxide. So there's our alkene. This alkene has 7 carbons. The starting material has 7 carbons. So we don't need to add any carbons. We simply need to take this leaving group and somehow make a double bond sort of more in the internal part of the molecule. So I think we can get that leaving group to leave, make this alkene. We know how to migrate alkenes now, so let's just do a Markov-Nikov addition. And now we can make the more substituted alkene with a simple Zaitsev elimination. We'd remove this H, which gives us the more stable alkene. And I'll use the smallest base I can to ensure that I get the most of this more substituted alkene. And then, of course, MCPBA plus the alkene gives me my desired epoxide product. All right, question 6. Here we have some specific stereochemistry, and we have this OTS group. And I think the only way I know how to put an OTS group on a molecule is to react tosyl chloride and pyridine mixed together with the appropriate alcohol. So let's look at that. And it doesn't change the stereochemistry. So now I have that alcohol, I've got this, and maybe there's certainly an H there. If we draw that in, it might become more clear as to what's going on here. You can see that the H and the OH were added syn. So maybe I did a hydroboration oxidation. To this alkene, adding H and OH to the same side of the alkene, and we made a racemic mixture, of course. So now the question is, how do I get this alkene from the starting material? There's an H right here. That's the one that I need to remove, I think. And actually, that's lined up anti-paraplanar to the chlorine. So I think all we have to do is use a small base. It would be good to convince ourselves of that. So let's draw a Newman projection looking along this arrow. And that would give me this as the front carbon, 1, 2, 3, 4. And then the back carbon would have a methyl pointing down, the chlorine over here, and the hydrogen. And this is the beta hydrogen I want to remove. This is the chlorine. They're in the correct orientation, right? So I can basically just take them off. And you see that the two methyls are cis to each other on the resulting alkene, as they are right here. So that's all I have to do, really, is eliminate and then add water in an anti-Markovnikov fashion using the hydroboration oxidation, and then tosylate. So I get this very stereospecific arrangement in my product. And the last one, chapter 12, is this one where I think we have 8 carbons. We have 8 carbons, so we don't need to add any. We somehow need to get this triple bond. We need to install the triple bond. And in order to do that, we need to do a double elimination to make 2 pi bonds. So we need the ability to do 2 E2 reactions. So we could have bromines like that, and then remove a bunch of hydrogens from the end carbon. I think it's probably going to be easier for us if we target the 1,2 dibromide instead of the 2,2 dibromide. So let's see if we can do that one. This one can certainly lead us to elimination, where we remove that H and remove that H, and that's that. So how do we do that? Excess NaNH2, followed up with water workup, 2 steps here. How do I get to this dibromide? Well, of course, that's simply Br2 addition to the appropriate alkene. Now, how do I get that alkene from the starting material? Well, of course, I could just do an E2 right there, Hoffman type elimination. I think I need a better leaving group for that, so let's do the first step, tosyl chloride and pyridine. That makes this an OTS. And then the second step, we'll use a large base to ensure that we get the Hoffman elimination, and that actually takes us all the way here, so we don't need any other steps. So again, you might count this as well, 1, 2, 3, 4 step sequence. But we can summarize it in a little more concisely. So that's, again, working backwards and figuring out how to make that as our first step along this process of synthesis.